It's the last day of this workshop, and I'm glad to see you all here. And the very first talk is a tutorial, the third tutorial, and it's given by Ruth Lieberman from GATS. And the title of the talk is Atmospheric Tides and Their Roles in Vertical Coupling.
Thank you all for being here this morning so early. I'd like to thank the CEDAR Organizing Committee for inviting me to give this talk. And I'd like to thank Sharon for getting us through slide number 1 in time-saving mode. So I will be speaking about atmospheric tides with emphasis on their roles in coupling. This is a tutorial. I took the request very seriously, and so I intend to begin at the beginning. Definitions, tidal sources, very simplified tidal theory. I want to talk a little bit about interpreting observations, figuring out how to mine tides out of observations. And then I will talk about the significance of tides, mostly in the middle and upper atmosphere, with emphasis on the roles that tides play in coupling among regions. So to begin at the beginning, as I said, atmospheric thermal tides, that's the category of tides we're concerning ourselves with today. Atmospheric thermal tides are global scale oscillations whose periods are fractions of a solar day. So we consider the 24-hour tide, the 12-hour tide. We can consider 8-hour tides and even 6-hour tides and so on and so forth. The ultimate source of thermal tides is the sun and is basically the daily sunlight function, which is switched on only when the sun is out there or visible to us on our side of the world, and is 0 at all other times. So since this function doesn't go negative, it's like a half cosine wave, it decomposes into a diurnal tide, which is the largest harmonic, a semi-diurnal, and so on. And I also just wanted to mention some useful nomenclature for anybody that is going to maybe get started reading about tides in the literature. It's very common in the literature to distinguish between tides that are migrating and tides that are non-migrating. And the migrating tides are quite simply the tides whose frequency wave number combinations work out to give a angular phase speed, a zonal phase speed of omega, Earth's rotation. So I've done the math for the diurnal and semi-diurnal tides. And a consequence of this phase speed situation, this phase speed formulation, is that it turns out that the phase of the tide can be naturally referred to local time. And so that's really the main distinction, is that migrating tides, their phases are generally referred to local time. And non-migrating tides are simply all other tides, frequencies, wave numbers, and so on, whose combination does not yield the angular phase speed of omega. And that includes tides going in the opposite direction. That includes tides whose phase speed is minus omega, or eastward. So before going any further, I thought it just might be illuminating to show a picture of tides. And so I'm showing here the diurnal and semi-diurnal harmonics of surface pressure tides. These are actual observations. The observations were compiled by Dai and Wang in a paper in 1999. I think they used about 25 years of hourly surface pressure records, the 25 years being needed for reasons you'll soon find out. However, recently Kurt Covey wrote a paper about tides and models, and he was helpful enough to sort of reproduce the Dai and Wang observations in nice color plots, so I just grabbed them out of his paper. So this left panel here is the diurnal harmonic and surface pressure. The color scale is such that the yellow maxima are roughly 150 pascals. And as you can see, the tide is global scale. It seems to primarily hug equatorial latitudes, although we do see it at subtropics as well. The magnitude, as I said, is about 150 pascals. Typical values of atmospheric weather surface pressure are 100,000 pascals. So to isolate the diurnal tide in surface pressure data, you're looking for something that's 0.1% of the background, so having 25 years of hourly observations helps. Left panel is the semi-diurnal tide. The color scale is different, so even though it's redder, these values are actually also about 150 pascals. But interestingly, the semi-diurnal tide is much more regular in longitude, has a much more longitudinally uniform structure, also seems to have a higher latitudinal extent, and we'll understand that better as we move on. So, tidal sources. Very important tidal source, particularly for the diurnal tide, is ultimately the tides originate with the sun, as I commented on, and so the question is, so the tides are originated depending on how the sun affects the atmosphere. So absorption of solar radiation in the near IR band by water vapor in the lower troposphere is a very big driver. I'm showing this here. The analysis is confined to tropical regions, most likely because my previous tutorial might have been emphasizing tropics. However, this is a function that does maximize in the tropical area. And as you can see, the amplitude of this heating, the diurnal harmonic of it, is very uniform in longitude, and its phase is also very uniform. And the arrow indicates the phase, the hour of maximum, which is, perhaps not too surprisingly, noon, local time noon all over the globe. So since this forcing is very uniform in local time, this actually is a main driver of the migrating tide, that tidal mode that I mentioned that depends on did I say universal time? Local time. These arrows are local time, hour of maximum. And the magnitude of this forcing is on the order of 10 milliwatts per kilogram. Another important driver, we've heard about this earlier this week, is the release of latent heat by deep tropical convection. There's a strong diurnal cycle to that. And this heating, I forgot to mention the solar heating was computed from a global water vapor set that NASA put together in the 1990s. This quantity, this latent heat release, was computed from trim rainfall. And so this looks very different than the water vapor heating. It's very regionalized. The heating hugs the continents and the maritime continent. There's a lot of longitudinal variation in amplitude and in phase. Over the continents, the heating maximizes at near noon. Over the ocean in the maritime continent in early morning. Its magnitude is about 1/2 to 1/3 of the solar heating. A third fairly well-known mechanism is the absorption in the ultraviolet by ozone in the stratosphere and O2 in the thermosphere. And this has great longitudinal uniformity. And so I'm not going to show latitude-longitude plots of that. I'm just going to show the quantities. These were computed in a model by Dave Ortland. And so it's just the zonally averaged heating in latitude versus altitude. So there's the ozone heating, which is about 50 milliwatts per kilogram, somewhat larger for the semi-diurnal. And this is the thermospheric heating, which is an order of magnitude larger. And then there's the EUV mechanisms in the thermosphere, the ionizing radiation. And I could only find a figure from Maura Hagen's 2001 paper. It's, I guess, not too easy to see these values, but it's occurring around 350 kilometers. And the units are already in watts per kilogram, so we're going up even an order of magnitude higher. And so after I prepared all those plots, I realized that I'd never really kind of thought about the relative values of heating at different altitudes. And so I thought it was interesting to note that the tidal forcing at the, closest to the surface is about 1/100th of a watt per kilogram, going up by an order of magnitude in the stratosphere, and by yet another order of magnitude in the lower thermosphere, and yet another order of magnitude, in the thermosphere proper. So we've spanned like, we've spanned like 4 orders of magnitude in the heating. Dynamics of atmospheric tides. From a dynamical standpoint, the tides are basically inertia-gravity waves on a sphere. So the restoring forces in a system like this are the Coriolis force and the pressure gradient force. And the momentum equations are further constrained by continuity and by the laws of thermodynamics. So this, actually doesn't look too bad of a system. But I find that I still find that it's easier to kind of understand what's going on if you can kind of cut the system down, simplify things down when and where possible. So for starters, I thought I would consider what the semi-diurnal tides how the semi-diurnal tides behave qualitatively in a region where the Coriolis force is not important, which is basically the equator and near the equator. Because in that latitude region, the semi-diurnal frequency forcing is much stronger than the Coriolis. So if we knock out that Coriolis term, then you're left with just the pressure gradient as a horizontal restoring force. And you can, compact these two equations even further by turning it into an equation for the divergence. And so at low latitudes, the semi-diurnal tides are just centers of divergence propagating, in this case, for the example I'm showing, westward. And these centers, pockets of divergence and convergence are simply chased by mass. So it's really they're basically gravity waves, internal gravity waves. So here's the semi-diurnal tide. This example as a wave number 2. The pseudo data comes from a tide model by David Ortland. And at low latitudes, we're seeing exactly what the equations predicted. We're seeing centers of divergence and convergence. And the divergence is chased by a quarter cycle later by a reduction of mass. This pattern propagates westward in time. So where there's divergence here, a quarter cycle later we'll have a reduction in mass, and conversely where the, did I get that wrong? Oh, here it is. And conversely, where the convergence is occurring, it's chased by an increase in pressure in mass. Not too bad. At higher latitudes, we're still on the semi-diurnal tides now. As you get higher, from the definition of F, the Coriolis parameter, as you move toward the poles, the semi-diurnal frequency and the Coriolis force approach each other. And so under those conditions, the pressure, the main balance is between the Coriolis and the acceleration, and the pressure gradient gets kind of marginalized. So it's a very different picture here. There's no more pressure gradient, really, and instead the restoring is done by the Coriolis term. And again, this can be compacted into an equation governing divergence in time, divergence tendency, but this time, instead of being chased by higher and lower mass, the divergence is chased by spin, by vorticity. This is called, and this kind of motion is called an inertial oscillation in textbooks. And so that's what's going on. We're here at the higher latitudes. The pressure perturbation is really fading out, as well as the gradient. And so we're seeing here that the convergence and divergence at one phase is being followed up quarter cycle later, basically by rotational motion. So that's the semi-diurnal tide. In the case of the diurnal tide, please note we have a different frequency here. It's omega, not 2 omega. Nevertheless, at low latitudes, we can still play the same game because diurnal or semi-diurnal, F is still 0 at the equator. So at the equator then, and very, very close to the equator, the diurnal tides behave dynamically very much like the semi-diurnal tides. I realize they look a lot different, but if you just focus on this equatorial cell here, the dynamics are exactly identical. Whereas in the case of the semi-diurnal tide, the divergence seemed to have a very strongly horizontal component. Here the divergence has a very strong north-south component to it, but nevertheless, the divergence is chased by low pressure and the convergence by high pressure. The thing is, however, is that relative to the diurnal period, the Coriolis force kicks in a lot faster. In fact, by 30 degrees, the Coriolis force and the Coriolis frequency and the diurnal frequency are equal. So we therefore make the transition to that inertial motion much, much faster. It's occurring by 30 degrees here, as opposed to the semi-diurnal tide where we saw it much higher. So the diurnal tide at low latitudes looks like a squished down semi-diurnal tide with a much stronger meridional component. Now, what happens at higher latitudes? As we move to higher latitudes, F, the Coriolis term, starts to exceeds omega. However, the largest F is ever going to get is 2 omega at the pole. And so the largest it ever gets is twice as big as the diurnal period. So we can never actually completely kill off these tendency terms. We can't ever totally ignore them. Nevertheless, it's still illuminating if you want to visualize what the diurnal tide should look like at high latitudes. It's nevertheless illuminating to visualize what a system looks like when the main players are the Coriolis force and the pressure gradient force. Anybody remember from Meteorology 101 what that's called? It's called geostrophic balance. And indeed, as you go toward higher latitudes, and I'm sorry to pull a southern hemisphere act on the audience here, but for the model pseudo data that I had, it so happened that the strongest response was in the southern hemisphere stratosphere. So as you're moving to higher latitudes with the diurnal tide, the motion is becoming more and more geostrophic, although it never technically reaches geostrophic balance. So there is the wind flowing parallel to the pressure contours. This being the southern hemisphere, the flow around the low is clockwise and counterclockwise around the high, exactly the opposite to the more familiar northern hemisphere. So I've talked a lot about the horizontal, about the behavior of the tide in the horizontal plane, and what's happening vertically. At the latitudes where the tides were shown to behave like pure gravity waves, they propagate vertically. For the diurnal tide, this is between 30 degrees north and south, and for the semi-diurnal tide, it's over the entire globe. And the main vertical wavelength of the diurnal tide works out to be about 27 kilometers, and about 60 for the semi-diurnal. And where they propagate vertically, they exhibit all the classical, vertical internal, wave propagation behavior. Amplitudes are increasing exponentially, theoretically, in the case of the tide, up to a point. For the diurnal tides, the exponential growth kicks in the stratosphere, but then by the stratopause, it really is tapering down to more of a linear growth, and then the tides saturate and break and so on at the mesopause. At the higher latitudes, the diurnal tides do not propagate vertically. And if there's in situ forcing like the stratospheric ozone at high latitudes, they'll be forced, they'll sit there, and their energy will leak away. And so I just wanted to illustrate this effect. This is, again, pseudo data from the model of David Ortland, temperature, zonal wind, meridional wind. And so at low latitudes, what I've done is I've taken the wave number 1 component and frozen it in longitude and time, so that you can see the changes in sign in the vertical at low latitudes, which indicate the vertical propagation. At the particular phase I chose, the ozone doesn't show up in temperature, but it does show up in the zonal wind, which kind of has a quarter cycle offset. And so here's the ozone response, which is high latitude and just kind of trapped, doesn't seem to propagate vertically. And that's basically it. And for the semi-diurnal tide, so I just wanted to point out this confinement of the propagation features to low latitudes. Now, in a real atmosphere with mean winds and everything, the meridional propagation channel can vary, it can widen. And so, the propagation is, it may be extending somewhat higher, but by and large, at high latitudes, you don't see vertical propagation of the diurnal tide. And this is the same model, but these are semi-diurnal tides. They propagate vertically everywhere, so I just basically, I'm showing the amplitude here. And it's clear that the semi-diurnal tide has a much broader, more global structure, since it vertically propagates everywhere. And just note, please, the vertical axis here, which is scaled height, goes up to roughly about 100 kilometers. And so I wanted to show you what's going on at higher altitudes, but rather than use a model result, I decided to showcase a plot that Charles McClandress published. These are thermospheric tides, or actually, it's just basically tidal signatures in thermospheric data plotted as a function of local time and altitude. This is about a month's worth of winds from the WINDII instrument on UARS. And between 90 and 110, the instrumentation was sensitive to both daytime and nighttime emissions. And so we have nearly full 24-hour coverage, which shows that diurnal tides are still pretty prominent, even though they're already kind of, saturating and damping here. And above 110 kilometers, where only daytime data was available, it's clear that the semi-diurnal tide is starting to really take over as we go from the high to low phase over a period of about 6 hours. And finally, just one last word about dynamics. I've kept it very heuristic, but I did want to mention atmospheric tidal theory. And what this does mathematically is it really just pulls together into one mathematical formalism all of this so-called F-plane behavior that I talked about earlier. And the way it's done is to apply the primitive equations with a windless atmosphere, U bar equals 0, and no friction. And when you do that, it turns out that the primitive equation system can actually be solved. And the solutions are series of spherical harmonics known as Hough functions. And so analytically, the tides are basically just expressed as series of global spherical harmonics that behave the way I described earlier. If you apply limiting factors to equatorial and high latitudes and so forth. So I just wanted to mention that for those who might go on to study tidal theory. And I also should mention that tidal theory, which is very elegant, was worked out mostly during the 1960s independently by Chapman and Lindzen and by Kato in Japan. And these two monographs are the granddaddies in the field. Observing tides. Sharon, it says 21 minutes here have elapsed. Does that sound right?
Yes.
All right. Observing the tides. This plot is a series of temperatures, zonal winds, and meridional winds taken from the sodium LiDAR at Fort Collins, covering 3 days in August 2002. And so this horizontal axis is the time, the hours, and the vertical axis goes, I think, from 80 to 100 kilometers. I intend to say nothing about what's actually going on there. That was in the Joe Shea's paper. I show this plot because it shows what I consider to be just about ideal sampling. I mean, as far as it goes, which is to say the LiDAR can only sample this limited altitude range. But this kind of sampling is about as good as it gets if you want to analyze tides. It's at a single point. It's continuous. It was made with an instrument sensitive to both daytime and nighttime signature. So we have a continuous, 24-hour sampling rate. I think it was hourly, probably even higher cadence than that. And so if you want to pull out a time mean, a diurnal, a semi-diurnal or more, then this is just great. It's perfectly straightforward. And ideally, we would have this kind of sampling over a vast latitude, longitude, altitude, and latitude, longitude, and altitude network all the time. We don't. I just threw up this map of ground-based facilities. I think this is fantastic. I think this is an amazing, network of facilities. But nevertheless, there's still a lot of gaps in latitude and longitude. Most of these facilities, many of them are, higher upper atmosphere, are lower mesosphere, lower thermosphere only. Some of them are not operating continuously. Some of them are sensitive to daytime only signals. Some are sensitive to nighttime only signals. So, we don't have the sampling that we want everywhere where we want it. There are resources out there that fulfill the requirements I've indicated. There are resources. Starting in the late 1990s, numerical weather prediction centers began to make available their global grids of the global grids of all of the variables they use in their models. They're called Reanalyses. Most of them output data on very dense latitude longitude grids, about 4 times per day. More recently, the MERA Reanalysis, I believe, outputs even 3 hours. What did I say? 4 times per day, 6 hourly. MERA is actually outputting their reanalyses every 3 hours. So, you know, I mean, that seems to be a pretty ideal setup. Good longitude coverage, good hour of day coverage, especially if it's 3 hourly. And in fact, reanalyses are, reanalyses are an easy way to get at the tides. And many people have, and it's all great, except the problem is that most reanalyses, even the best ones, and for me, by best, I mean the ones that go up the highest and that report the most often, even the best reanalyses don't get above 60 kilometers. And so it doesn't really solve the upper atmosphere problem. And although I don't want to go into this, you could go into the whole question of how well an analysis from a forecast model, how much it's really telling you, especially as you get to its highest levels, because you know, at the diurnal period, I mean, for diurnal and semi-diurnal tides, they're probably going to be bound very, very much to the model, and not so much to the observations. But nevertheless, there's a lot of useful information that can be gotten out of reanalysis, and about a year ago, Sakazaki et al. Intercompared diurnal tides, possibly semi-diurnal as well. He intercompared the tides in 6 reanalyses with CEDAR, and it's a very useful paper for anyone who wants to do more with this. GPO, you know, temperatures from GPS radio occultation receivers have been going up a lot in recent years. And I'm not going to show the results of those. I'm just actually showing you the sampling patterns and local time that can be obtained from constellations of GPS receivers that supply temperature. I mean, for tidal purposes, the temperature would be the useful quantity. And so, you know, so talk about latitude-longitude coverage. Well, we're getting, you know, plenty of that from the cosmic constellation. And you know, there's pretty good local time sampling. It may take a few weeks to collect it. But, you know, it might appear that GPS is a partial solution to our dilemma. If you're concerned, you know, with the altitude range of GPS data, which seems to top out at about 35 kilometers. Above the GPS and reanalysis levels, the most comprehensive spatial sampling is still being given by satellites. And CEDAR, which I've shown here, is probably one of the best known ones that's still up there. And so it would appear that CEDAR is solving all of our sampling problems. It gives very comprehensive sampling in latitude and longitude. This is just one day of observations. But the problem with most middle atmosphere satellites is that their orbit is configured in such a way so that they only provide two local times a day. And these local time crossings are actually the satellite vehicle. If the sensors on the satellite are able to pick up emissions during all hours of the day, then this kind of sampling would buy you 2 local times a day of measurements. And many sensors are sensitive only to daytime, or nighttime only, or daytime only. So we've got good spatial sampling with the satellite, but you know, the temporal sampling is so-so. Nevertheless, you can actually still learn a lot, under certain circumstances, even with limited local time sampling. For example, I've shown here data from the Hardy satellite, from the Hardy instrument on UARS. They measured winds in an orbit very similar to CEDAR, in terms of the sampling stuff. And I've filtered the data so that the only thing we're seeing here is longitudinally averaged wind. So I've gotten rid of, I've gotten rid of transient perturbations and non-migrating tides. And if you want to look at a quantity which has no competition when you in terms of daily longitudinal averages, if you're looking at a quantity that's the only game in town that has no other competition, then even having only that one local time is still very useful. This corresponds to the migrating diurnal tide and meridional wind. This represents only one local time. But in the latitude and altitude plane, you can still learn a great deal about it. You can tease out an amplitude, you can infer vertical wavelength, you can infer, after a fashion, temporal behavior. So, so it may not be so bad having, limited local time sampling. However, the problem is that if you're dealing with variables that have very, very strong background components that compete for the tide for attention, then it can be harder to get the tidal information out, like temperature, for example. I mean, if you're only viewing the temperature at one local time a day, this is zonal mean temperature, it's not going to be easy to find the tide in this. As it turns out, there's a signature of it here and here, but it's like 1% of the background. Now, many satellites are in sun-synchronous orbits, meaning that this kind of local time sampling is it. The two local times picked up here on this plot are the only two local times that you're ever going to get from them. The LIMS satellite is like this, the EOS-ORA satellite is like this, the AIM satellite is like this. So what do? Well, one old trick that is to form a tidal proxy, a diurnal proxy, by subtracting the field, the measurements made at the two different local times. And again, because of orbital characteristics, they're often close to 12 hours apart. Maybe they might vary between 10 and 14 or so. So the trick of inferring a diurnal tide by looking at a 12-hour difference, or something close to it, is a very old one. It actually goes all the way back to the 60s, where Mike Wallace subtracted daily radiosonde measurements made at 0 and 12Z and inferred diurnal tides. And the same trick was applied to satellite data, starting with Hitchman and Leovy in '85. William Ward has done this with Krista data. This particular plot I made here uses data from the MLS instrument on EOS-ORA. And so a 12-hour difference will also tell us a good deal about the tide. It certainly highlights the vertically propagating behavior we've talked about at low latitudes. And so, that's what you do. That's one thing you can do if you want to study tides in sun-synchronous satellite data. However, many satellites precess, thankfully. So that's nice because they pick up extra local times. And so that clearly that clearly provides an advantage in defining the diurnal tide more conventionally. So the UARS satellite picked up 12 daytime hours over 36 days. And I'm showing again Hardy winds here in the mesosphere and lower thermosphere. Hardy was sensitive to only to the daytime emissions over most of this altitude range. So you're only getting, you're only seeing the picture during the daytime, but nevertheless, a good deal of useful information can be obtained. The timed satellite collects 24 hours over 60 days. The wind instrumentation was improved so as to provide nighttime coverage over more altitudes. And so the tides have been analyzed from time data by many people, including Xiaoli Zhang and Oberheid and Shen Wu. Lots of nice work done by them. The CHAMP satellite collected thermospheric winds, sampled 24 hours over 140 days, and Zhang et al. Used the stratospheric radio occultation temperatures to get tides in the stratosphere. It was a proof of concept for the cosmic mission. And Hausler and Lohr have done a lot of tidal analyses with this kind of data. So with that, I am moving on to answer some questions that possibly might have occurred to some of you long before this, which is, why are we doing this? Why are tides important? So the answer is, in the mesosphere and lower thermosphere, the tides are practically the strongest possible motion, the strongest motion in the atmosphere, with maybe a couple of competitors like the two-day wave. But the tides are always there, and they are pretty much some of the strongest motions out there. So for that reason alone, it's worth knowing how they behave. And as you can see, sampling can be problematic. And when you've got a huge thing out there that can possibly be aliasing, your signals, it's a good idea to know something about it. Another consequence of the tides being very large in the mesosphere and lower thermosphere, especially the diurnal tide, is that the diurnal tides are saturating and breaking at the mesopause level. And in doing so, they transfer their momentum to the background wind. In the case of the migrating diurnal tide, one of the stronger modes, the migrating diurnal tide transfers westward momentum to the zonal mean flow. What does that look like? This is a plot, again from Hardy. It's actually 3 years of zonal mean wind data on this axis, and this is altitude. And it's actually quite a comprehensive plot going from the lower stratosphere all the way up to the lower thermosphere. It was made by Mark Burridge. And for the purposes of the one point, though, that I'm trying to make with this plot is that in the layer between, say, about 95 to 105, this layer is one of permanent westward zonal mean winds, where I indicated the line. And the diurnal tides are almost certainly maintaining this structure here, because they pump daily, 5 to 15 meters per second per day of acceleration into the background wind. Tides modulate useful, important aeronomical species. This is a plot. I seem to be showcasing Hardy here a lot, aren't I? This is a plot also taken from Hardy of the O2 night glow emission, plotted as a function of local time and latitude. And there's a very strong local time modulation of this emission. And it was parsed. It was parsed by Dan Marsh, and who pointed out that the vertical motions associated with the tide move atomic oxygen, abundance up and down over the day, which influences, O2 and hydroxyl recombinations. And the reaction rates are also modulated by tidal temperatures. And more recently, in fact, just yesterday, Jens showed us how certain tidal modes, these are examples of non-migrating tides because they're propagating eastward. Jens showed us how certain key non-migrating tidal modes are modulating nitric oxide volume emission rates, and this is a very important gas for the thermospheric heat budget. We talked earlier about the tidal vertical wavelengths and how they're long, relatively speaking. And these long wavelengths make the tides very efficient agents of vertical propagation, and more to the point, transmission of information about the troposphere to higher altitudes. I mean, we've been hearing a lot about this all week. But one example, so I've got several examples of this. The first one is from a study that, can everybody still hear me? I know that when speakers turn toward the screen, the amplification can be lost. Okay, good. So here's an example. This plot shows 16 years worth of tidal amplitudes in meridional and zonal winds measured by the MF radar at Kauai. And these amplitudes are at 90 kilometers and Kauai is 20 north. So we noticed a spike in 1997-98, and since that happened to be an El Nino year, we wondered whether the two events might be related. And to make a very long story short, the answer, we believe, is yes. I know this is a busy plot. Please actually look at the right-hand side first. What I'm showing here is the diurnal water vapor heating. We talked about that very early in the talk. That's a very powerful diurnal tide forcing mechanism. And the thing to notice here is that in 1998, there is a very strong perturbation from the time mean value, from the time mean picture of this heating pattern. And it actually kind of has an uncanny resemblance to some El Nino indices that you might run into. And now if you move over to the left-hand panel, you will see that normally the Eastern Pacific is cold and dry, and so there is a hole, if you will, in the diurnal water vapor forcing. There's spatially there's kind of a bite taken out of that heating pattern in the Eastern Pacific. This looks kind of weird, but that is the normal. That's the climatology. In 1998, because the Eastern Pacific was warm and more moist, there was more water vapor over that region. There was more heating, and from the point of view of the diurnal tide, there was a much more even, much more uniform, heating going on that year, which forced a stronger migrating diurnal tide. Not going to go through this, but you see that's what that blip there is in 1998. And that elevated the response of that elevated the migrating tide response to H2O heating in 1998 relative to other years. And so we believe that this is we believe that this suggests that the El Nino can kind of imprint itself upon the diurnal tide at least as high as 90 kilometers through this water vapor heating mechanism. And we only investigated this issue up to the lower thermosphere, but I know that more work has been done on El Nino-induced tidal variability by Oberheid and his student Warner, and by Nick Petadella. Another example of tropospheric imprinting, if you will, is this so-called DE3 mode. This DE3 corresponds to the eastward propagating diurnal tide with the wave number 3. It so happens that this mode this wave has a very long vertical wavelength, about 56 kilometers, and so it survives well into the thermosphere, more readily than other tides. And this is a plot using WINDII data from UARS, and these are thermospheric winds going, well, actually I've added Hardy on the bottom for continuity. But these winds are going up to about 250 kilometers. This is the amplitude of DE3, and so DE3 is still going pretty strong, even at 160, and it hasn't even really faded that much by the time the data gave out. And this mode has been shown quite definitively to be forced by the deep tropical convection. And one more example of the DE3 imprinting can be seen in this plot, which is kind of becoming an iconic image in our own time. This is brightness from, well, this is a brightness signal given off by, I don't know what you call O+, ionized oxygen. The Berkeley fellows will correct me if I get this wrong. But this imprinting of DE3 was observed by an emission that corresponds to the 350 kilometer level. And do I have any more examples of that? Oh yes, and finally, one more example of this DE3 imprinting can be seen in the work of Hausler and Lohr. This is a power spectrum, as a function of tidal wave number by month. Their data represents the 350 kilometer region, its zonal winds, and they also see not only an eastward 3, but they're also seeing an eastward 2. And so, as I said, tides are efficient agents of coupling and tropospheric imprinting. And to follow up on this issue of tidal coupling, in addition to being able to couple vertically, as we've seen, tides, because of their global structure, can also couple phenomena in one hemisphere to the other. And this is thought to play a role in the, this is thought to play a role in the, stratosphere, ionosphere connections. So everybody by now, I'm sure, has seen these split vortex plots, so I'll skip that eye candy. But, and everyone, I'm sure, has seen this plot many times this week, but I'm not going to skip it. This plot of the vertical drift at Hikamarka in January 2008 shows the drifts over several days. Those are the colored curves. Over several days surrounding a strat warming event in January 2008. And the solid curves are sort of the climatology of this quantity. And so clearly there were some strong perturbations that coincided with the warming. And this strange behavior, for lack of a better phrase, was observed not just at Hikamarka, but also over a wider area in total electron content data sets. And it just shows that, during this, relative to a control or a climatology, I guess, there was some strongly perturbed behavior, not only over Hikamarka, but over all of South America. And the perturbations are not only, kind of amplitude perturbations, but there's also phase shifting going on. The experts can say they are better at this, but I believe that one of the main changes is that the drift is occurring at, earlier in the morning. relative to business as usual. And so, of course, there's a lot of work being done currently to try to see if there really is a link with sudden warming. I mentioned several mechanisms here, but I'm really not going to elaborate on them. There's been speculation about increased ozone concentrations during warming, forcing stronger semi-diurnal tides. There's been discussion about the role played by the lunar tide, which is very unclear. But what is clear is that the lunar tide seems to matter in numerical modeling efforts to replicate the ionospheric observations. And then finally, the mechanism that I'll focus a little bit more on here, which is nonlinear interaction between planetary waves and diurnal and semi-diurnal tides, which generate additional families. I see it. I've got 15 minutes. Which the nonlinear interaction, creates kind of a family, creates a new generation of, child waves, if you will. And so these child waves, some of which have efficient propagation characteristics, can modulate the overall 12 and 24-hour amplitudes and the E region dynamo. So I don't know if I need to, this eye candy is basic. This eye candy just shows a picture, just shows a picture of that. The interaction will be facilitated if the planetary waves that result in the warmings. The interaction is facilitated when the planetary waves are ducted equatorward, which is generally the way they behave, because the waveguide toward the equator is more friendly, to their propagation. And so you set up these child, diurnal tides that propagate into the ionosphere. So what I have been working on lately then is to see whether some of these predicted child waves are actually there, are actually being seen in the atmosphere, are actually attending sudden warmings, or maybe not even the sudden warmings, whether they're actually attending the planetary wave amplifications that lead to sudden warmings. And so I've just looked briefly at some data from the Navy's assimilation. They have a model that goes up to 90 kilometers, and they gave me actually some hourly output. And so all I'm going to mention here, I know it's hard to read the axes. This is the planetary wave, the strong planetary wave 1 that was seen in early January 2009 in the stratosphere at high latitudes. The big bright spot is at like 60 degrees, but it actually is kind of nosing toward the equator. This is latitude here. And here is one of these child waves predicted to occur from nonlinear interaction, a DW2. And all I want to say at this point is that DW2 seems to track, this planetary wave in time. And I do believe that it is forced to a certain degree. I don't have figures. I didn't bring figures to prove that point. But nevertheless, DW2 has other sources other than the nonlinear interaction. So a lot of work is still required to determine how much of what we're seeing here really could be related to the planetary wave. That's in the works. And so finally, I just want to say, that the process that I verbalized, the upward, let's go back to the eye candy, the upward propagation of these child tidal modes into the ionosphere, where they then perturb the dynamo and perturb the E cross B drifts. This whole mechanism has been numerically investigated by Han Li and has basically been shown to be perfectly plausible in the sense that it occurs in his modeling experiments, and just about everything that was thought to occur occurs. There's of course nuances, in the modeling results. I'm not going to go into that. But this mechanism certainly appears to be plausible insofar as models show it, produce it. And so that's really, pretty much it. I thought I would wrap this up by just making a few statements about, challenges for tidal research that, in tidal research that didn't really make it into the body of the talk. So, for example, I've certainly impressed upon you that tidal sampling is, kind of a challenged area, and that right now, in order to understand what's going on throughout the entire atmosphere, throughout the entire throughout the entire vertical atmosphere and over the globe, we need to really patch together different data sets and assimilations and model results. And hopefully the upcoming ICON and GOLD missions are going to close some of these gaps, and we will be hearing more about those later on this morning. Another big challenge in understanding tides is understanding tidal variability. There's some very intriguing seasonal and interannual variability, in particular a possible QBO tidal modulation. And these are simply not understood, despite almost 20 years of 20 years of efforts to do so. It's just not. It is simply not clear why the tide varies this way, and since the variation of the tides are tracking variations in the zonal mean wind, it's natural to perhaps explore the effects of background winds on tides and on these variabilities, but it's not as easy as it sounds, and so we still don't understand it completely. And then one other challenge that hasn't gotten a lot of attention here is that it's a real challenge for numerical models to simulate the observed vertical structure of the diurnal tide, particularly the wavelength. It just doesn't. It's just not easy to do, and it's almost certainly tide gravity wave interaction plays a role, and so that's yet another thing that still remains to be done. And so I am finished here early. Thank you all for coming.